And that page is page 11. Okay, so that's page 11. And we'll just number as we go. If you've already numbered, that's great. It'll just save you a little bit of effort. And again, my apologies for not getting those numbers in there before I sent it to the print shop. That was really irritating, but there we are. All right. So if you want to have a substance that can conduct electricity, you need to have two things. First thing you have to have is you have to have charged particles. Okay, so that's number one. And if you want to have something that can conduct electricity, those charged particles have to be able to move. So you can't just have charged particles, they also have to be mobile. Okay? So we're going to look at a solid ionic compound. And actually, let me see if I've got it here. Should be back in here somewhere. Yep, there it is. Do you see this lovely blue crystal? This lovely blue crystal is copper 2 sulfate. And if I were to tell you to write the formula of this, what would you need to know? Copper is, what's the symbol for copper? Cu. And what is the symbol for sulfate? Does anyone remember? It's SO4, okay? What is the charge of the copper? It's 2+ because that tells us it's 2+. And if you were to look on your polyatomic ion sheet, you would see that copper sulfate was SO4, 2-. So while I go get my conductivity apparatus, you guys are going to write the formula for copper 2 sulfate. There we go. All right. So hopefully you remembered that in an ionic compound, the charges have to balance. You have to have the same positives as negatives. So your formula would be Cu SO4. 1 Cu, 1 SO4. Now, what I'm going to do is I'm going to turn on this conductivity apparatus. Right now, I'm not sure if you can see it. Can you see how there's 2 wires here? And you see how the wires are not touching? So this is not a complete circuit, okay? And the light bulb does not light right now, so I'm going to turn it on, and you can see that if it's just air, the light bulbs do not light, right? So you need something conductive to attach the one wire to the other wire. So what I'm going to do is, I think I'd like a pair of tweezers. Let me just grab a pair of tweezers. Or so much smarter, silly me. What I can do is I can place this back in its little dish because I don't actually want to come in any danger of actually touching the wires myself, because We, as human beings, are full of charged particles that can move. So if I were to touch those two things, it would very happily let me conduct the electricity. So I don't want any chance of that happening. So what I'm going to do is I'm going to hold this in the little plastic dish, and I'm just going to bring it up, and I'm going to touch it to each part of the wire. And what happens? Absolutely nothing. It is so exciting, right? So that is our ionic compound. And this is in its solid form. So we have our ionic compound, and it is solid. So I'm going to ask you the two questions. Does it have charged particles? Does an ionic compound have charged particles? Yes. What are they? What are the charged particles in an ionic compound? Ions. Can those charged particles move? I see Fernando shaking his head. Why not? Because it's a solid, right? Within a solid, particles don't move from here to there. They just jiggle a little bit, right? They're locked in place. And if you remember, we've got our crystal lattice structure. The ions in a solid are fixed. In other words, they can only jiggle. Jerry, you're distracting me. Logan, you're also distracting me. Okay, so these particles can only jiggle, they cannot move. So we can say, can those charged particles move? The answer is no. And if you cannot say yes to both of these questions, then it will not conduct electricity, as we just saw. Nothing happened, right? So you have to have charged particles, and they have to be able to move. Here we had, yes, we have ions, but no, they cannot move. And so the bulb, this is a little picture showing what the bulb does, and there's no glow. Yeah, it's just nothing. Ionic compounds, however, if we melt them, and I don't have a beautiful picture of a melted one, and I can't melt this here. I can't melt this here because how high would I have to heat it to melt this ionic compound? I would have to heat it to like hundreds of degrees Celsius. Does that seem very safe or energy efficient? No. So I'm not going to do it, but you can imagine, just like when water melts, the particles, rather than being locked together, they can now move. So I would like you guys to show me two solid particles. And they're jiggling. Jiggle, jiggle, jiggle. Jiggle, jiggle, jiggle. But they can't move. They're just jiggling. And now it melts. Okay, so when it melts, they can move here, they can move there, they can move anywhere they want to. So now we have an ionic compound. Does it contain charged particles? And the answer is yes, because we already knew that. Can they move? And the answer is yes, because now they are melted. Okay? And if you had a positive metal plate, which is positive, And if you had a negative metal plate, the negative charges, and you can see the negative charges are the ones that are blue, they would move towards which side? They would move towards the right-hand side. Okay, so all your negative charges are going to move that away. What about your positive charges? Which direction are they going to move? Positive will move to the left towards the negative and away from the positive. Okay. I might ask you to label a diagram like this with the arrows showing the movement of the ions. Yeah? Does that sound reasonable? Okay. And you can see, here's a little picture showing some molten NaCl, sodium chloride. What does molten mean? Molten means melted, yes. I can spell melted, sure I can. Melted, there we go. Molten means melted. And you can see we've got some metal rods. We've got it attached to a positive terminal and the negative terminal. Which direction are the electrons moving? Are the electrons going to move clockwise? Or are they going to move this? I'm talking about the top of the circuit right now. Or are the electrons going to move counterclockwise? So this would be clockwise. This would be counterclockwise. Tell your partner what you think. If you agree, that's great. If you disagree, try to convince each other. So if you think they move counterclockwise and your friend thinks they move clockwise, see if you can convince each other which way they're going. Okay, what do we think? Clockwise? Counterclockwise? I don't know yet, which is a perfectly acceptable response. Anyone I don't know yet? That's fair? Okay, absolutely fair. So what we've got is we've got a battery here, and you'll notice that this terminal of the battery is the positive terminal. That means that end of the battery has more protons than electrons. The negative terminal of the battery is over on the left-hand side, and it contains more electrons than it does protons. So when we have electrons in the wire, this negative pushes the electrons, and it keeps pushing them. And this positive pulls electrons. Okay, so this positive charge over here pulls the electrons. And what that means is that the whole thing is all the electrons are going to be moving counterclockwise as they are pushed from the negative terminal and pulled towards the positive terminal. And our light bulb, because this thing contains positive ions and negative ions, the bulb will glow. There's our bulb, it's glowing. And in our molten sodium chloride, Which direction will the chloride ion move? Will it move to the right or will it move to the left? Which direction is our chloride ion going to move? Have a little think about that. Which direction will our chloride move? Is it going to move to the right or is it going to move to the left? Anyone have any ideas? Anyone think they know? You don't have to explain it to me. You guys think it's going to move to the right? Anyone agree with them? Okay, let's think this through, yeah? What's happening is electrons are leaving this metal rod here. Let me grab a green highlighter. Electrons are leaving the green metal rod, which makes it a little bit positive, yes? Which means that the chloride is going to move towards that positive charge. And it all goes in the same thing because the negative charges, the electrons, move counterclockwise. Does it make sense that the negative ions also move counterclockwise because they are the same charge as the electrons? Everything negative should be going in the same direction. That's that way for you guys. I have to remember I'm backwards from you. This is counterclockwise for you, right? Yeah, okay. Yeah, so if we flip the battery over, what would happen? Is that the question? Yeah, if we flip the battery over, the light bulb will still light, but the electrons will go the other way. But it doesn't matter which way the electrons are flowing. And in fact, when you take physics, like real physics, you will learn about something called conventional current. Way back, hundreds of years ago, when they were doing experiments with electricity, they were like, okay, we don't know what's in there. This was before the atom, right? So this was in the 1800s, before they really thought about the structure of the atom, before J.J. Thomson, before all of that. But they're like, we know there's positive and negative things, and we think that it's the positive things that move. In fact, they didn't even really think that. They just said, let's say it's the positive things that move. Okay? And so textbooks were written, formulas were devised. There's a right-hand rule where if the current goes this way, the magnetic field goes this way. And all of this is very wonderful. And they did all of these things. And then they were like, okay, let's define the proton as being positive, not realizing that the protons stayed in place. And then let's make the electrons negative, not realizing there was the electrons that move. What they really should have done is make the protons negative and the electrons positive. If you think about the word positive and negative, they're just the opposite of one another. They could have defined it the other way around, right? They're just words that we gave to it. So they kind of messed things up. So when we learn about it in grade 9, because we understand electrons, we're going to talk about the flow of electrons. But if you take physics, it's the flow of positive charges, which is going to be backwards, okay? And positive charges don't actually move, but if you're showing current in a physics class, in physics 11 or physics 12, you're going to show it going the other way around. And you know what's kind of fun though? If we look at our sodium, which way does the sodium move? It moves to the left. Because it is attracted, because we've got electrons coming in here, so that's going to be a little bit more negative. The sodium's actually going to move there, and it's actually going to grab an electron and become neutral sodium. So it will neutralize all those extra electrons that end up there. And so you can actually see that that positive charge is actually moving in the opposite direction to the negative charges. Okay, you are not responsible for conventional current, the positive charge flow this year, but it is interesting to know about because it's one of those historical things about science where they just define things in a weird way that made it awkward. Okay. Next page, if you have not yet labeled it, this is page 12. So if you've not labeled it page 12, you want to label that page 12. What happens to ionic compounds when you dissolve them in water? Do you guys know? When we take NaCl and we dissolve it in water, it actually splits up into Na plus ions and Cl minus ions. So if you were to see sodium chloride in water, instead of having a crystal lattice, the Na plus ions would float around separately from the Cl minus ions. And there would be water in between them. Okay? So when you dissolve ionic compounds, you end up with freely floating ions. Do you guys remember what it's called when something is dissolved in water? Aqueous. So we would say this is NaClAq, which stands for aqueous, which means dissolved in water. If we take a look at that beaker full of water, so we got water in the background, and we got Na plus ions floating around, Cl minus ions floating around. Let's ask ourselves those two important questions. What are the two questions you ask yourself if something will conduct? Number one, are there charged particles? Question number two. What's question number two? Can they move? Are there charged particles? Can they move? Are there charged particles in there? Yes. Can they move? Yes. Okay, and you can see we've written that up here. Do we have charged particles? Yes. Can they move? Yes. Shall we see what happens when we actually have a solution of sodium chloride? I'll go grab some. Okay. Let's see, where's my sodium chloride here? You kidding me? That's okay. All right, here's my sodium chloride. All right, here we go. Let's see what happens. Remember, this is on right now. Here we go. Ooh. Yes? Yeah, there's a little teeny tiny one up at the top, right? So you get a nice bright light experience from that. This is just some water that I'm going to use to wash this off. Do you think the water is going to conduct electricity? Think about that. Make your prediction to yourself. And now we're going to check it. Nothing. We'll talk about why in a little bit. Okay? So, conformation, an ionic compound that is dissolved in water will conduct electricity. You can see here we have a battery. And, dang it, what did I do with my pen? There it is. And we have our salt solution. And in our diagram, the negative ions are moving to the left. So we would have negative ions in here and they would move to the left. There are positive ions that move to the right. So we would have a positive ion and it would move to the right. If that's the case, which of these two terminals of the battery, this is like a 9-volt battery, I don't know why it's round instead of square. You know those batteries that have like the two terminals on the top? You know those ones? Okay, that's what we got here. Which one of those is positive and which is negative? Based on the motion of the ions. Which one of these is positive and which one is negative? The right one is? Actually, I should start with the left one because we usually label things on the left first. What would the left one be? Positive. And the right one would be negative, because the negatives are attracted to this positive, and you can imagine the electrons. Which direction would the electrons go? Would they go clockwise or counterclockwise? Clockwise. They're going this way this time, right? And our light bulb, lo and behold, it glows, just like we saw in our little demonstration a minute ago. We're not going to watch this video right now. If you're interested in ionic compounds, you can watch that video. We are now moving on to where it says metals at the top of the page. This is page 13 if you've not yet labeled it. And I'm going to go grab a stick of copper. Okay, did not find copper, but I found aluminum. What type of element is aluminum? It is a metal. Shall we see if it conducts electricity? What do you think is going to happen? Okay, let's find out. Okay, so metals do indeed conduct electricity. Why? Do they have charged particles? What are the charged particles in metals? Metals contain electrons and protons. Can any of those move? Yes, which ones can move? The electrons. Can all the electrons move? No, just the valence electrons can move. Okay, and this now takes us back to metallic bonding, right? Because if you remember, you've got those cations with all the valence electrons just like going everywhere. But if you put a positive here and a negative here, they can all go in one direction. Yes? Okay. There is, what do we call this area with all of these valence electrons in it? What is the name that we give to this? That is called the sea of electrons. Remember, you have a quiz on this tomorrow, so this is good review for your quiz tomorrow. Those valence electrons, how do we say that they can move? We say that they are mobile. And there is a word for not stuck in one place. Delocalized, yes. So the word for not stuck in one place is delocalized. So we have our sea of electrons, which is made of mobile valence electrons, which are delocalized. And so if we have our wire, there's our wire, and the electrons are all moving in different directions. You can see this is where there's no charge on either end. You've not hooked it up to a battery. And they're moving left, they're moving to the right, they're moving to the down, they're moving to the right, they're moving diagonally, they're moving every which way. So this is in the absence of an electric field. But the moment we put up a negative on one side and a positive on the other, all of those electrons start moving in one direction. This would be a great picture for you to illustrate on a quiz about conductivity, which will take place on Friday. Yep, they're all really tiny. They're like, this one's a half a page. I think the conductivity one is just a little bit longer because there's a few pictures in it that you have to like draw on. So it'll be bigger simply because there's like diagrams. Okay. So we have a quiz on (6.1a) on Thursday. We have a quiz on 6.1b on Friday. Okay, and this is metallic bonding. And this one is conductivity. There is one rewrite per quiz, okay? Not like a million rewrites, but one rewrite per quiz. Putting arrows on a diagram like this would be a good question. Okay. Now, I'm not sure when you would have a situation like this, but if you have a metal that happens to be liquid, it still has mobile valence electrons. So liquid metals are also conductors. And once again, I'm not going to demonstrate a liquid metal because hundreds of degrees Celsius, dangerous. But liquid metals, just like solids, they have mobile valence electrons. Yes? Do you know what? That is actually a bit of a myth. They are slightly, very slightly further from one another than a solid. But they're still very close to one another. That is a really good question because I feel like when it's liquid, it's hotter, so maybe the electrons are able to move faster. But I don't know for sure. I would have to do some reading up on that because I know as you heat up a wire, conductivity get greater or less? I think it gets greater as you heat up a wire. But then what happens when it turns to a liquid? That's another question entirely. I would have to do some reading on that. I'll take a look and see what I can find. Yeah. Okay. Yeah, absolutely. By the way, if you come up here, just don't come too close to this thing because, you know, if you like bump it with your arm, not good. I mean, it won't kill you. I've done it by accident. It's just a little painful. Okay. It's not pleasant. Okay. So if we have a molecular covalent substance, when things are covalent, what happens with the electrons in a covalent substance? The electrons are the electrons between the atoms are shared. Okay, so if I had, let's just do the most simple molecule we can think of. If I have a hydrogen, right, and I've got a positive nucleus, and it's got a single electron, and I have a second hydrogen that has positive nucleus and a single electron. How many electrons fill up the first shell? 2. Yes? So both of these hydrogen atoms would be more stable if they had 2 electrons. So what they are going to do is they are going to get together and they are going to share those 2 electrons between them so that they each get a full valence shell. does it look like those electrons are able to move? No. And even if we get other structures that have more electrons in them, like here is water, right? We've got oxygen, which has got some inner electrons. It's got 8 electrons on its outside shell. None of those electrons are able to move. They can't jump from one water to another. They're stuck to that water. All those electrons are stuck in that molecule. In fact, they occupy very specific orbitals and they cannot move out of those orbitals. But as long as you know they're stuck in position and they cannot move, then you've got the general idea, okay? So although we have charged particles, we have protons, yes. We have electrons, but can they move? Can the protons move? No. Can the electrons move? No. So, do you remember when water did not conduct electricity? Right? Where'd my water go? Here it is. That's because water is a neutral molecule. Okay, it doesn't have an overall positive or negative charge, and it doesn't have any protons that can move. It doesn't have any electrons that can move, and that's why it does not conduct electricity and is super boring in the demonstration. So you have an unlit bulb. Now, the rest of this is enriched stuff. Actually, no, we got one more. That was enriched, but we do have one last one. We can have aqueous molecular covalent. So this is like sugar water. Okay? Sugar is a covalent compound. Wow, why is it? Sugar is a covalent compound. Yes. And when sugar dissolves in water, let's take a look at what this is our ionic compound. Has free floating ions. And you can see there's negatives. Those are our chlorides, maybe. We have our positives. Those are sodiums, probably. But over on the right, we've got sugar dissolved. Do you see any charges on the sugar? No, sugar is neutral. All its protons and electrons are locked in place. So the moral of that story, out of these two solutions, one of them can conduct and one of them cannot. Which one can conduct? The one on the left. Our ionic compound can conduct. And the one on the right cannot conduct. Okie smoky? All right. And then I think all the rest of the stuff is enriched. Let's just double check. Yeah, covalent network solid, diamond, graphite. It's really interesting if you're into it. And if you want to ask me any questions about it, feel free. But we'll get to the exercises. The exercises are on page 19. So find the one that says exercises, and you're going to label that page 19. Okay? And you guys can do the exercises on page 19 and 20. We'll leave 21 for next day. Okay? So that is the exercises 6.1b, exercises numbers 1 through 8, which is pages 19 and 20. Okie dokie? Yeah, for sure. And if you need a little break, if you need to stand up, if you need to